Okay, let's look at this example. So we have here a circuit with two resistors, one inductor and one capacitor. So in this case we have a switch, all right? So the switch here is closed before t equals 0, but at t equals 0 the circuit or the switch will open, right? So the question asks to calculate or to find the voltage across the capacitor here, right, in time domain. So V, voltage across the capacitor in time domain at for t more than 0. So what is the voltage across the capacitor when the t is more than 0, meaning that when the switch is open? Before t equals 0 the switch was closed, and now when the switch is open, what is the voltage across the capacitor, right? So first thing is we need to know that when the switch is closed, right, at t less than 0, the switch is closed, right? So meaning that we have a complete circuit when the switch is closed. We have the inductor here, and then we have the capacitor here. So this is when t is less than 0, and we have here 20 volt supply. Now because of the constant voltage supply, we know that at a constant voltage supply, inductor will become shorted and capacitor will become open, because the capacitor, when the capacitor is fully charged, it is similar to an open circuit, and when the inductor is supplied with a constant source, it will become similar to a shorted line. So basically we can redraw the circuit, okay, because of the constant source. So now it is become this, shorted and then open, right? So the reason why we need to analyze when the circuit is t less than 0, when the switch is closed, is because we need to find the initial condition, all right, initial condition for the inductor and the capacitor. Okay, as we have learned in the previous videos on the Laplace transform circuit analysis, that the inductor and capacitor has their own initial condition. Depends on the question. If the question tells us that you can assume the initial condition is 0, then there is no initial condition. But if there is initial condition, then you have to take that into the calculation. But in this case, the initial condition is not given, all right, but you will have to calculate the initial condition yourself, right? And that is when t is less than 0. That is the initial condition of the inductor and capacitor. So now we are trying to find out, or trying to determine what is the initial condition for the inductor and capacitor. So since the switch is closed, then the inductor is shorted, capacitor is open. So we need to find what is the initial condition of the inductor, what is the initial condition of the capacitor. So here this is the initial condition of the inductor, and this is the initial condition of the capacitor, right? So this is the initial condition, right? Now we can calculate the initial condition of the inductor, which is the current that flows here, right? So that is basically the current here, right? To here, to here, to here, to here. So since this branch has a resistor, so the current will not flow here, the current will only flow here. So that is this is 5 ohm, this is 20 volt. So basically the current here is I L0 is basically 20 volt divided by 5 ohm. That is 4 amp. And what about the voltage of the capacitor? Voltage of the capacitor, that is the initial condition, that represents the initial condition of the capacitor. Now, since this branch is shorted and this is also the same voltage polarity or voltage terminal, sharing the same voltage terminal, so this is simply 0, right? So we know that VC is 0, right? So that is the initial condition for the inductor, right? The inductor is shorted, so that is the initial condition for the inductor. And then for the capacitor, it is the same terminal with this branch, so this is 0 volt, so this is 0 volt, right? Now once we have determined the initial condition for the both inductor and capacitor, we can continue with when the circuit is right at t more than 0, after t is 0, after the switch is open. Now when the switch is open, now what we have is only the resistor, inductor and the capacitor. We have the resistor, which is 1 ohm. We have the inductor, which is 0.25 Henry, and we have the capacitor, which is 1 farad. This is during t more than 0, but we have initial condition for these two components, right? Now we can redraw this circuit in S domain, right? So we can redraw the circuit in S domain. So when we draw the circuit in S domain, this is still 1 ohm, and now the inductor is 0.25 Henry times S, and then the initial condition of the inductor, which is represented by a current source, right? Now this is 4 over S, right? Remember, it is I over S, right? So this is 4 over S, and then we have the capacitor. We have capacitor, but since the capacitor has no initial condition, which we have calculated earlier, 0, right? 0, then no initial condition for the capacitor. However, the value of the capacitor is 1 over S. This is the value of the capacitor in S domain, right? Now we need to find the voltage across the capacitor. Right? We need to find the voltage across the capacitor. Here what we can do is we can use Kirchhoff current law. Right? Kirchhoff current law. Right? So we assume that all the currents going to the ground, right? So all the currents here moving away from this terminal Vs, and there is no current going into the terminal Vs, so that we can write this equation. That is, all the currents going out this point equals to all current going into this point, right? That is, here we have Vs divided by 1 plus Vs, put here, Vs divided by 0.25 S, and then we have, this is the current, right? This is the current. So in order to get the current, we have to use take the voltage from here to here, which is Vs, divided by the resistor, right? V divided by the resistor will get the current. This is the current V, right? This is the voltage divided by the impedance, which is 0.25 S, will get the current. Or let me try to rewrite this. Right, Vs minus 0 volt here, minus 0 volt divided by 1. This is the current. Vs minus 0 volt, right? This point here minus this point here, voltage minus voltage here, divided by the impedance here, 25S plus, alright, here no need to do the voltage divided by impedance or voltage divided by resistors, because we already know the current, which is 4 over S, and then in this case this is Vs over 1 over S, and then 0, because there is no current going into the terminal, or this not, right? Now we can rearrange all this. Okay, let me just simplify the equation. Zero. Then we can basically SVS minus 4 over S, and then we can, and here is equals to 4, right? Right? For Vs over S, right? And then this one is basically just equals to Vs, right? So now what we have is Vs. Let me just try to simplify this. 4 over 4 plus 1 plus S, Okay, equals negative 4 over s. Okay, and then this is actually, bring this to here, we will get s squared plus s plus 4, and then equals to minus 4. Right, check that first. We have s here, we have 1 here. Oh, sorry, this is 4 over s. This is 4 over s, right? 4 over s, and then we bring here to here, we get s squared, we'll get s, we'll get 4. Yep, right. And then let's continue. Let me piece of paper. Right, continue. Vs equals to negative 4 r squared plus s plus 4. Right, so basically we just move all this to here, right? And then this is where it gets a little tricky, right? The whole point here is later on we will need to perform inverse Laplace. Okay, we need to perform the inverse Laplace. So typically what we can do is we can use check on the equation first. All right, okay, right. So basically what we can do here is try to have it in such a form, like have a s plus b squared plus a squared, right? Now this is from inverse Laplace transformation or Laplace transform pairs basically, right? So if we have, let me just write this again. Right, let me just, one example is e negative at cos omega t, right? Okay, we form Laplace transform, we will get sorry, not cos, it is sine. Okay, we'll get omega over s plus a squared plus omega squared. So this is taken directly from the table, Laplace transform pairs table, right? So what we can do is try to rearrange this term into this format. Okay, now let's look at the how we can do that. So continue here. So first is, okay, so how can we arrange this into s plus a squared? All right, so we know that this is s squared plus something squared, right? Now to get 2 times s plus something to get s, that is 1 over 2, right? 2 times s plus something should get us s. That is 2 times s times 1 over 2 will get us s. Alright, and then 1 over 2 squared will give us 1 over 4. So we have to minus that, right? And don't forget this plus 4. Okay, so if we try to calculate this, what we will get is s squared, and then 2 times s times 1 over 2 will get us 2 times s times 1 over 2, and then this is 1 over 4 minus 1 over 4 plus 4. So so basically we will get cancel. Oh, this is plus. We'll get 4, right? So same value. So we just rearrange or represent it in a different way. Okay, so once we have done that, now we still have to work on this. Now we have this format s plus a, okay, squared. All right, s plus a squared, but we need to work on this. All right, so meaning we have to combine this into one value, s plus 1 over 2 squared. So this is can now have 4 times 4, 16 minus 1, that is 15, so plus 15 over 4, right? And then to make it squared, you simply square root this value and then put square here, right? So we'll get square, right? Now we are almost there. The problem here is this omega must be this omega, so this value here must be the same as this value. So that is not a problem. Okay, we can just simply add this value up here, but in return we have to add this value as well here. So that is let me show you. 4, take this value, bring it up here, 15 over 4 square root s plus 1 over 2 square plus 15 over 4 square root square, right? Since we put it up here, we also have to put it at the back here to compensate, right? Okay, because if we cancel this, we will get the same as this. All right, and then from here we can bring this to the back so that we can clearly see now that this term is looking exactly as this. Right, or let me just rewrite this again. So Vs is now minus 4 over 15 over 4 square root times 15 over 4 square root s plus 1 over 2 squared plus 15 over 4 square root square, right? And now we see that this is, we can just simply do inverse Laplace to get this, right? Okay, finally this is Vs, which is negative 4, 15 over 4, 15 over 4, plus 4 square root square. So inverse Laplace Vs to get the Vt, right? And that is this, which is exponential of negative at. Right, but before that we have to bring it to the front here. So this is constant value, right? And then now we can inverse Laplace this term. That is exponential negative at, or exponential negative a, which is from here, right? So exponential negative a from here, which is 1 over 2, but 2 t, and then sine omega t, which is omega is this, sine omega t, which is omega this value t. Okay, of course this is in volt. Therefore the voltage across capacitor is this value.